Hello, folks. We're back to a sequence here with new content where you guys are going to be getting a bunch of videos coming up. And I'm sorry about the number of videos. It's just this is the only way I can really get the information across to you guys. And so I have to break it up into a bunch of smaller ones instead of one very, very large video. So anyway, let's go ahead and get started with this next piece of content and then we can go from there. All right, so the next topic is on how waves, we've talked about how waves propagate and just being a vibration. So right now we're just going to stay focused on waves on a string for the next few days, and then we'll get into other types of mechanical waves after that. But when we have waves that are propagating along and then they encounter a boundary, we're going to have a reflection that occurs off of that boundary. So there's 4 different types of reflections that I want you guys to know, and 2 of them are very similar to each other. So really broken down into 2s, but there are 2 sets of them. So anyway, you will need to understand fixed end reflections, free end reflections, and then reflections that occur from a less dense to a more dense medium, and then a more dense to a less dense medium. So what I'm going to do is go ahead and start, and we'll come back to these diagrams here and kind of walk us through them. But I want to go through this website here real quick and kind of go through all of the different types of wave reflections. All right, so if we have a rope attached to the wall and it's fixed boundary up against the wall and I snap the rope one time, the wave will propagate towards the wall, but then it's going to reflect off of the wall. Since it's fixed into place, what's going to happen is there's going to be a complete 180-degree phase shift on the reflection. So as you can see in this illustration here, the wave has a positive amplitude that is incident upon the wall, and then when it reflects, the wave flips over 180 degrees out of phase with the incoming wave. All right, so this does cause some interference here, and we will talk about that here in a little while. If we have a soft boundary instead, or a free end reflection, so now imagine instead of the rope being affixed to the wall, we have like a little ring around it and we just drop it over a ring stand. If we snap this rope as it gets to the barrier with the free end reflection, notice now that the reflected wave is in phase with the incident wave as it comes in. Okay, so these 2 are opposite. Fixed end, free end reflection. Fixed end reflection, 180-degree phase shift. Free end reflection, the reflected wave is in phase with the incident. When I say incident, I just mean incoming. All right. The other 2 types, ignore all of those, is let's say instead of having one rope fixed to the wall, we now have a thin rope attached to a thick rope. So basically what's happening here is we're going from a less dense medium to a more dense medium, okay? As the incident wave comes in, this is very similar to a fixed end reflection, but we also, since this is just another rope here, we have partial transmittance of the actual wave. So some of the wave continues to propagate through the second rope, but we have a reflection that occurs at this boundary to where the reflected wave is once again 180 degrees out of phase with the incident wave. Then we have just the opposite of that. We have a more dense to a less dense medium. Incident wave is reflected very similar to a free end reflection. So what we have here is the incident wave is reflected in phase with the incident, and then you have the wave that continues to propagate through. I don't care, and we don't need to get into as much detail on why this one has a greater amplitude, but just understand that the transmitted wave, reflected wave, and the incident waves are all in the same phase, okay? All right. Once again, this is just another diagram here showing exactly what happens. We go from less dense to more dense. Just a review, so the reflected wave is out of phase. Some of the wave is transmitted through. If we go from more dense to less dense medium, the reflected wave is in phase with the transmitted wave and also with the incident wave. Okay, so just make sure we understand those 4 types of wave reflections. All right, so here's the next term. What we saw was wave reflections for a single pulse. If we have multiple pulses of a wave that are incident upon the barrier, when they strike the barrier and reflect off, there's also going to be multiple reflections or continuous reflection. So the wave's going to sit there and move back and forth and back and forth and back and forth. Now, if the conditions are met for a standing wave to form, you will end up with a wave pattern that appears to stand in place. So hence the term standing wave or stationary wave. If the waves are of equal wavelength and frequency that are incident and reflected, then you will get a standing wave or stationary wave pattern to form. Okay, and I'll show you what this looks like here in a little bit. I got a bunch of cool demos to do at school, but obviously we can't do those right now. So I'll have to use the computer to kind of illustrate this. When we get a standing wave form, this is basically what's going to happen. You get these series of nodes and antinodes. At the nodes, basically the displacement at that point, so if you can imagine having a wave on a string like this, it reflects off and it comes right back through like this. These nodes, you have no displacement whatsoever that occurs. These are regions of maximum destructive interference. At the antinode regions, this is where the maximum amplitude as the waves constructively interfere with one another, and you get these regions of maximum constructive interference where the amplitude is double usually than the wave that comes in. Okay, so I'll show you this here in just a little bit. All right, so when the standing wave patterns form, this is what's called resonance. So we can shake a rope up and down, make it reflect off the wall. If we don't reach a specific mode of vibration or a specific frequency, we will not get a standing wave that generates. So when we have resonance occurs, then a standing wave forms. And resonance occurs when an object or a medium vibrates at one of its natural modes of vibrations or one of its natural modes of frequencies. This can be any object that generates a waveform, okay? One thing I remember is an old video, I think from back in the 70s or 80s, maybe in the 60s. It's called the Tacoma Narrows Bridge. You can actually Google it and find a YouTube video on it. The wind begins to blow at just the right speed that causes the bridge to start swaying back and forth at one of its natural modes of vibration. And when that happens, the bridge continues to sway more and more and more until eventually the bridge collapses. Okay, same thing can happen with a tall building. Okay, if the wind blows hard enough and the building starts moving back and forth, if you get one of the fundamental modes of vibration, it can cause the building to crumble from that. Another example of this, if we're thinking about a sound wave, if we have someone that can sing at the right frequency and you're near a plate of glass, if that vibration pattern gets established in the glass at one of its fundamental modes of vibrations, it can be strong enough to crack the glass. Okay, so this doesn't just apply to waves on a string. This applies to all types of waves. Okay, so at resonance frequencies, the medium vibrates at a standing wave pattern. Now, there's going to be different modes of vibration. So for a string, the first mode of vibration is called the fundamental frequency. So any string that vibrates at its fundamental frequency would basically, if you can imagine, and I'll show you a picture in here in a little bit, if you can imagine having a rope attached to the wall, the fundamental frequency is just like it would look if you were jumping rope. Okay? So you'd have the nodes at the two ends and then the antinode in the middle. Anything beyond that are overtones of the fundamental frequency. So the fundamental is called the first harmonic. The second harmonic frequency is the first overtone of the fundamental. Okay, so what I'm going to do is jump to handout 842. I have this posted on Canvas, so you guys have it. All right, so I'm just going to focus on the front page here. The back page is closed and open tubes. We'll get to that next week. Waves on a string. So to get a wave oscillating in a standing waveform on a string, once again, the fundamental looks like a jump rope. So this is basically going up and down here, and you have your nodes on the end. So this is just oscillating up and down. Okay, notice that this right here is exactly 1/2 of a wavelength. So the length of this string right here is the wavelength divided by 2. Remember, the wavelength is symbolized with a lambda. So this is the fundamental mode of vibration for a string. If we increase the frequency of this string, we can reach the second mode of vibration. So now we have where it's oscillating up and down here and oscillating up and down here. But if we just focus on the blue line here, notice this is exactly one wavelength. So the length of this string here is lambda. So this is the second harmonic frequency, which is the first overtone of the fundamental. We can continue adding half waves by increasing the frequency more and more and more. And now we have 3/2 of a wave. So the length of this string is 3/2 of lambda. Okay, so this is the second overtone of the fundamental, or otherwise called the third harmonic frequency. Okay, so these are things you're going to have to be able to know, because remember, one wave is from here to here. Okay, this is 3/2 of a wave. So the length of the string is 3/2 of lambda. So that means lambda is 2/3 of the length of the string. So which makes sense, because lambda is from here to here. So this is one wavelength. So these are things that you'll have to be able to calculate out. Okay. All right. I'm going to quickly get moving on here. And here's basically what happens when we're talking about harmonic frequencies. All of the, so if we just thinking about a single string, if we get different standing wave patterns to form on that string, and we have multiple strings vibrating at different standing wave patterns, as long as they are all vibrating at one of the harmonic frequencies, we can then overlap all of those vibrations to form a repetitive wave. So notice that we have this frequency, which is the same, and then we have a different frequency here that's vibrating. But when we overlap these three frequencies, because they are all harmonics of the same fundamental tone, we end up with a pattern that, even though it looks a little garbled, it is repetitive. If instead we have three different strings vibrating at different frequencies that are not of the same harmonic, then we get a non-repetitive tone. Okay, so this would be like having a guitar string that is out of tune and then trying to overlap the sounds. It does not end up producing a very pleasing sound quality. Okay, so what we want is this repetitive harmonic frequencies to overlap and form this repetitive waveform. Okay, I'm not sure how much time I have here, so I'm going to go ahead and stop this video and then do another quick demonstration on the second one. So I'll start a new one here in a second.